Acha, so up till now we have been learning about prisms or diffraction through surfaces. Now what we'll start is refraction through lens or lens. So our first question, what is lens? Lens is nothing but an optical device that passes through or lets the light pass through. Suppose this out here, this is a lens. You can have magnifying glass, that is also a lens. So what are usually lenses? Lenses are nothing but devices that are shaped like this. Okay, out here, light from one side, light from one side, passes onto the other side. Okay, passes onto the other side. Or lens can also be shaped somewhat like this. Light from one side passes onto the other side. Light from one side passes onto the other side. If we trace this back, they appear to meet. So lens that have this kind of shape, okay, are called convex lenses. Lenses that are of this kind of shape are called concave lenses. Problem is, or how do we define lens, or what is the mathematical definition of lens? So listen carefully, okay? Lenses are nothing but a union and intersection of two solid transparent space. What do I mean by that? See, what do I mean by that is, see out here. You see this surface? Acha. This much amount of lens is made up of glass, no? And this much amount of lens is made up of glass. So suppose I take a solid sphere of radius R1. Radius R1. And I take another solid sphere of radius R2. Then the intersection between these two spaces, this space is nothing but a convex lens. Okay. Similarly out here, if I take two space, a sphere of radius R1 and a sphere of radius R2 and a sphere of radius R2. A union of these two spaces gives us a concave lens, or a union of these two spaces gives us this kind of lens. Okay, fair and fine. Okay. Problem is, why did we define this lens by this surface? But this surface is nothing but radius of this curvature. This surface is nothing but radius of this curvature. This surface is nothing but radius of this curvature, and this surface is nothing but radius of this curvature. So this kind of optical device, transparent optical devices, are called lens. One more thing you have to learn out here. See, convex lens is not only of one type. There are many types of convex lenses also. Suppose I take a lens like this, okay, it is joined by a straight wire. So this kind of lens are called, these kind of lenses are also called convex lenses. Acha. So the first type of convex lens is usually biconvex lens. Biconvex lens. Okay, and this one is biconcave lens. Concave lens. The second type of lens, or this type of lens, okay, is made up of union of a sphere of radius R1 and a plane surface, and this union, acha, I made the intersection at the incorrect junction. Let me make it at correct junction. The radius of R1 and a straight line. So this intersection will be called this length. Similarly out here, okay, out here, This kind of lens also can exist. Okay, we trace the ray backward, it will meet at a point, or it will appear to meet at a point. So these kind of lenses are made by union of a sphere of radius r1 and a straight line. Okay, but this union is nothing but the lens, but this intersection is nothing but the lens. So this kind of lens are called plano-convex lens, plano-convex lens, or plano. This kind of lenses are called plano concave lenses. Okay, now the third type of lens that I'm going to study is, suppose a lens that is made by this one. Okay, how are these lenses made? This is the focus. This lens is made by nothing but intersection of two space, a sphere of radius r1 and another sphere of radius r2, and this region is nothing but the lens out here, and this type of lens is called acha. For the concave counterpart, I'll draw in the next page. Okay, so this kind of lens out here is called concavo convex lens, and for the counterpart, and for the concave counterpart, the concave counterpart is nothing but a lens made by somewhat like this. Okay, okay, a ray of light goes out here, a ray of light goes out here, it appears to diverge, so it diverges, and if we see the image from the opposite side, it appears to converge at this point. Okay, so this type of lenses are made from two space of radius r1 and r2. Union of these two spaces is nothing but the lens. Union of these two spaces, or these spaces, is nothing but the lens, and this kind of lens is called convexo-concave lens. Convexo-concave lens. Okay, now you are going to issue an misnomer. See, behavior of a lens in, or behavior of a lens in refracting a light, or why is the behavior of a lens. Okay, out here, see, all biconvex lens, concavo-convex lens and plano-convex lens will behave in the same manner. Okay, so suppose a convex lens is there. Okay, any parallel ray of light incident on the lens will converge some point after refraction, and this point is called focal point or focus. Okay, and this is nothing but focal length. This is nothing but focal length. But does the ray always behave like this? No. Why? See, suppose this lens was made up of glass and this was made up of UA. Okay, so this type of shapes only behaves as a converging lens only when mu of glass, or refractive index of lens material, is greater than refractive index of medium in which the light travels. Okay, similarly for concave lens or this type of lens, okay, a ray of light, parallel rays of light diverge after refraction and appears to meet behind the lens at focal point. So this out here is nothing but the focus, while this is nothing but the focal length. Okay, okay. But this only happens when the prism is made up of glass and the medium is made up of air. Or refractive index of the lens material, sorry, refractive index of the lens material is much greater than the refractive index of the medium in which the ray is traveling. Or refractive index of glass is greater than, sorry, refractive index of lens is nothing but refractive index of glass is greater than refractive index of air. So for the lens to behave somewhat like this, the refractive index of the lens should be greater than the refractive index of the medium. But what happens when the refractive index of the lens is lesser than the refractive index of the medium? What happens then? Acha. So suppose refractive index of the lens is lesser than refractive index of medium. That means what? That means suppose I conduct the same experiment with lens underwater. Okay, underwater. Now the same shape of lens. Okay, but instead of glass, this lens is made up of air, and this entire lens is made up of is inside water. So this medium is nothing but kept inside water. So we know that refractive index of air is much lesser than refractive index of water. Refractive index of water. So how will light behave out here? See, a converging lens, when refractive index of lens is lighter than refractive index of the surrounding medium, will behave as a diverging lens. A convex lens will behave as a diverging lens. And similarly, a concave lens, when the refractive index of the lens is much lesser than the refractive index of the medium, will behave as a converging lens. Okay, but the lens was made up of air and we are conducting our experiment underwater. Understood this part? Okay. Acha. Now what we're going to learn is the determination of focal length of lenses, or determination of focal length of lenses. Acha. To determine focal length of the lenses, what we use is we use the formula for curved surface. Okay. So suppose first let's define what is focal length. Suppose this is a convex lens. Okay. Acha. Rays coming from infinity. Rays coming from infinity will converge at a point. Okay. And this is nothing but focal length of the lens. Okay. And similarly for this kind of lens, rays coming from infinity would appear to converge at a point, and this length is nothing but focal length. So how to derive focal length? Okay, see, if we zoom in on this surface, or if we zoom in on this surface, okay, acha, this surface, this entire system of lenses is made up of three surfaces or three changing surface: surface 1, surface 2, and surface 3. So this entire system is made up of two refraction. Okay, refraction through surface 1, refraction through surface 1, and refraction through surface 2. So let me go into detail. Suppose I'm zooming on this surface 1. This is surface 1. or surface 1 out here, and I'm separating this via imaginary boundary, and this is surface 2. Okay, this is surface 2. That means this out here, this surface out here, and this surface out here is surface 1. This surface out here is surface 2. Okay, surface 2. Okay, problem is how do I determine focal length of these lenses? See, if this material is made up of refractive index, I can simply apply the principle of refraction from curved surface. And what is the principle of refraction from curved surface? My cold. What is the principle of refraction from curved surface? There's some medium, there's some lens. So I can simply say across curved surface, across this surface, if I apply principle of refraction, or mu of lens by V minus mu of medium by U is equals to mu L minus mu M divided by R. So in this surface, this side is considered positive, this side is considered negative. Achha. U is nothing but infinity for the object. Okay, U is infinity for the object. So can I simply say, or mu of lens by where the image is formed at lens for this curved surface. For this curved surface, there is an image formed somewhere out here. So that is given by V is equals to mu of lens minus mu of medium divided by R. Okay. Now the main thing actually occurs out here. You always have to remember what the image formed. Acha. Now what we're going to learn is the determination of focal length of lenses, or determination of focal length of lenses. Asha. To determine focal length of the lenses, what we use is we use the formula for curved surface. Okay. So suppose first let's define what is focal length. Suppose this is a convex lens. Okay. Asha. Rays coming from infinity. Rays coming from infinity will converge at a point. Okay. And this is nothing but focal length of the lens. Okay. And similarly for this kind of lens, rays coming from infinity would appear to converge at a point, and this length is nothing but focal length. So how to derive focal length? Okay, see, if we zoom in on this surface, or if we zoom in on this surface, okay, Achha. This surface, this entire system of lenses is made up of three surfaces or three changing surface: surface 1, surface 2, and surface 3. So this entire system is made up of two refraction. Okay, refraction through surface 1, refraction through surface 1, and refraction through surface 2. So let me go into detail. Suppose I'm zooming on this surface 1. This is surface 1 or surface 1 out here, and I'm separating this via imaginary boundary, and this is surface 2. Okay, this is surface 2. That means this out here, this surface out here, and this surface out here is surface 1. This surface out here is surface 2. Okay, surface 2. Okay, problem is how do I determine focal length of these lenses? See, if this material is made up of refractive index, I can simply apply the principle of refraction from curved surface. And what is the principle of refraction from curved surface? My cold. What is the principle of refraction from curved surface? there's some medium, there's some lens. So I can simply say across curved surface, across this surface, if I apply principle of refraction, or mu of lens by V minus mu of medium by U is equals to mu L minus mu M divided by R. So in this surface, this side is considered positive, this side is considered negative. Achha. U is nothing but infinity for the object. Okay, U is infinity for the object. So can I simply say, or mu of lens by where the image is formed at lens for this curved surface. For this curved surface, there is an image formed somewhere out here. So that is given by V is equals to mu of lens minus mu of mu of medium divided by R. Okay. Now the main thing occurs out here. You always have to remember what the image from the first surface. Okay, the image from this surface will form out here, will act as an object from the second surface. So always remember, not only for two surfaces, for any multiple device. Okay, for any multiple device, that means two or more devices, just follow the incident ray from first. Follow the incident ray from first device, then second device. Just follow the incident ray to the first device, second device, third device. Device means nothing but lens or mirror. Okay, so for any surface, for any multiple reflection or refraction, or refraction, the image from the first surface, from the first surface. Okay, the image from the first surface is nothing but what? The image from out here. Okay, so the image from the first surface or first device. Suppose there are multiple lenses, or suppose there are multiple mirrors. So instead of first lens, just do first device. Okay, will act as an object. Will act as an object for second device or second surface. Second device or second surface or device. Okay, so out here, this is surface 1. So this is surface 1, and surface 1 will have radius 1, or the radius of surface 1 is R1. Okay, and this is surface 2. This is surface 2. The radius of surface 2 would be R2. The radius of surface 1 is R1. The radius of surface 2 would be R2. Now if I consider same sign notation, plus or minus, see, sign notation should be added in terms of lens. Suppose it is convex lens, so you add, suppose this is convex lens, so surface 1 is plus R1, surface 2 is minus R1. Suppose you have concave lens, so surface 1 is minus R1, surface 2 is plus R2. Okay, so mu by V, mu L by V is equals to mu L minus mu M by radius of surface 1. Now let's focus on the second surface. Okay, for the second surface, for second surface, we can simply write mu M. Why mu M? Because the image is forming in medium. Mu M by V2 minus mu L by U1 is equals to mu M minus mu L by R2. Okay, what is V2 out here? V2 is nothing but the focal length. Okay, V2 out here is nothing but the focal length. See, out here in this entire first and second surface will converge a image or will converge a object from the infinity to the focus, no? So image is at infinity and object is at infinity and image should be at focus. Okay. Or mu m by f minus mu l by mu1 mu2 for surface 2 it is mu2, for surface 1 it is mu1. Acha, mu2 is equals to mu m minus mu l divided by r2. Now problem is, what is this mu l by mu2? Okay, mu l by u2. See, this u2 is nothing but v1. Why? Because the image from the first surface will act as an object from the second surface. So mu l by v1 is nothing but mu l by u2. So can I substitute this entire thing out here? Yes, I can substitute it. So if I substitute it, what will it become? Acha. What will it become? It will become mu m by f minus mu l minus mu m by r1 is equals to mu m minus mu l divided by r2, or mu m by f is equals to mu m minus mu l divided by r2 plus mu l minus mu m divided by r1. See, out here mu l minus mu m, can I multiply this entire thing by minus? See, I can multiply this entire thing by minus and this also can be minus. So mu m by f is equals to mu m minus mu l by r2. Achha. Or let's do the reverse thing. Okay, let's multiply this entire thing by minus. Let's multiply this entire thing by minus, or minus 1 into minus of mu m minus mu l divided by r2. Why am I multiplying by minus? We'll see a little bit later. Okay, plus mu l minus mu m divided by r1. So it's nothing but, if I multiply this minus into mu m minus mu l is nothing but mu l minus mu m. Okay, or mu m by f is equals to minus mu l minus mu m divided by r2 plus mu l minus mu m divided by r1. So if I take mu l minus mu n common, or mu m by f is equals to mu l minus mu m common, then 1 by r1 minus 1 by r2, or 1 by focal length is equals to mu l by mu m minus mu m by mu m is nothing but 1 into 1 by r1 minus 1 by r2. This is the focal length of a lens. For this out here, what I have derived is the Lensmaker formula. Acha, the thing to remember in Lensmaker formula, always use sign convention. Okay, that means what? That means for positive lens or any lens, plus minus, plus minus. So out here, this is surface 1, this is surface 2, this is surface 1, surface 2. Out here r1 is negative. Why? R1 forms in the r1 is positive. Why? R1 forms in the positive side. R2 is negative. Why? R2 forms in the negative side. Similarly for concave lenses, R1 is negative. Why? R1 forms on the negative side, and R2 is positive. Why? Because R2 forms on the positive side. You have to see the curvature of the lens. You have to see the curvature of the lens. The curvature of the lens of R2 has on positive side and the curvature of lens of R1 has on negative side. The curvature of surface 1 is on positive side and the surface of curvature 2 for convex lens is on negative side. So see the curvature. Okay. Acha, the next thing that we are going to learn is power of a lens. Okay. Power of a lens. So what is power of a lens? See, this power of a lens, this lens is nothing but how powerful or the ability to converge or focus the rays from infinity. So power of a lens is nothing but 1 by focal length. Focal length. Okay. The formula for power is nothing but 1 by focal length. Acha. Out here, that means smaller is the focal length, more powerful is the lens. Okay. But how do we calculate power? See, power is equals to 1 by focal length, but the condition is this focal length should be measured in meters, should be measured in meters. So suppose I have a focal length of acha. So power is nothing but 1 by focal length. Acha. So power is nothing but, or the unit of power is nothing but 1 by meter, or unit is nothing but 1 by meter or meter inverse. This 1 meter inverse can be also known as 1 diopter. Okay. So suppose I have a lens whose focal length is 25 centimeter. Focal length is 25 centimeter. That means rays from infinity converge 25 centimeter from the lens surface, or 25 centimeter. What is the power of this lens? Acha. Power of this lens is nothing but power is not 1 by 25. You have to first convert this 25 into meter. 25 by 100 meters, or is equals to 0.25 meters, or 1 divided by 0.25 meters will give us 1 divided by 0.25 is nothing but 4 meter inverse, or meter inverse is also known as diopter. Okay. Achha, so let's read the question. Okay. Let's solve a few questions from this theory. A plano-convex lens of unknown material and unknown focal length is given. With the help of a sperometer, we can measure the. Achha. A sperometer is a device that is used to measure the radius of curvature. Okay. Suppose sometimes it is not possible to measure full radius of a sphere. We are only given a curvature of a sphere. So a sperometer is a device that is used to measure the curvature of curved surface, or radius of curvature of curved surface. Okay. Now let's read this question. The power of a biconvex lens is 10 diopter and the radius of curvature of each surface is 10 centimeter. Then the refractive index of the material is, if power is given, power is equals to 10 diopter, then focal length is equals to, power is equals to 1 by focal length, no, or 10 is equals to 1 by focal length, or focal length is equals to 1 by 10 meter. Or how do I convert 1 by 10 meter into centimeter? Focal length is equals to 1 by 10 into 100 centimeter, or is equals to 10 centimeter. Okay. Now can I apply Lensmaker formula? Yes. The Lensmaker formula is 1 by focal length is equals to mu of a diffractive index of lens divided by refractive index of air. Out here I am considering the refractive index of air to be 1 and I am considering the lens to be operating in air. So mu L by 1 minus 1 divided by 1 by R1 minus 1 by R2 says the formula. Okay. The power of a biconvex lens. Biconvex lens means this type of lens. Okay. So this is surface 1, or biconvex means also means that R1 is equals to R2. This is surface 2. Surface 1 is positive R. Positive R. Okay. Surface 2 is negative R. Negative R. Okay, so 1 by f is equals to mu l minus 1 divided by 1 by r, minus and minus becomes plus 1 by r, or 1 by f. Now let's substitute the value. What is the value of f? 10 centimeter is equals to mu l minus 1, 1 by r plus 1 by r becomes 2 by r. What is the value of r? The value of r is 10 centimeter. See out here. Why did I convert meter to centimeter? Now you understood, because out here 10 centimeter and 10 centimeter would get cancelled. Or 1 by 2 or 1 by 2, okay, is equals to mu l minus 1, or 1 by 2 plus 1 is nothing but 3 by 2 is equals to mu l, or d is equals to 3 by 2. Now let's check this question. Okay, a double convex lens has a focal length of 25 centimeter. Okay, the radius of curvature on one of the surfaces double the other. Find the radius if the refractive index of the material is mixed. That means one of the surface is double the radius of other surface. So if this surface is radius 2r, this surface is radius r. One more thing I forgot to say is that doesn't matter the order of surfaces. Okay, suppose the first surface has radius r and the second surface has radius 2r, r and 2r. The magnitude of focal length would be same. Okay, the value of f would be same. The magnitude of focal length out here would be the magnitude of focal length out here. Okay, it does not depend upon the orientation. Okay, so can I simply apply one lens maker formula? 1 by f is equals to mu l. What is the value of mu l? 1.5. The lens is operating in air, so the refractive index of air is nothing but 1, minus 1 into 1 by r1, or 1 by 2r, minus of minus 1 by r. Why minus 1 by r? Because first or second surface has radius in negative side. If I consider this side as positive and this side as negative, second surface will have in negative region, no? Or focal length is nothing but 25 centimeter. So 1 by 25, 1.5 minus 1 is nothing but 0.5. Acha. Out here, let me simplify the equation instead of substituting out here. Okay, let me keep this as f only, or 1 by f is equals to, let me keep this as mu l by mu a, mu l by mu medium, or mu l by mu medium minus 1. Acha, it's 1 by 2r plus 1 by r. If I replace this, 1 by f is equals to mu l by mu m minus 1. If I take 1 by r common, 1 by 2 plus 1 into 1 by r, or 1 by f is equals to mu l by mu m minus 1 into 3 by 2 r. Okay. Now what is this? 1 by 25, or 1 by 25, or 1 by focal length. What is the refractive index of lens? 1.5. Refractive index of air by 1 minus 1 into 3 by 2 r. 3 by 2 into 1 by r, or 3 by 2 r. Now can I send this r to the left hand side and 25 to the right hand side? So r is equals to 1.5 minus 1 into 3 by 2 into 25. Okay, or r is equals to 1 by 2 into 3 by 2 into 25, or is equals to 75 by 4, or 18.75, or is equals to 18.75 centimeter. 18.75 centimeter. So r1 is equals to 18.75 and r2 is equals to 2 into 18.75, which is 37.5. Acha. Okay, let's read this question. An equiconvex lens is cut into two halves along XOX, that means along this line, and along YOY, as shown in figure. Let f, f dash and f double dash be the focal length of complete lenses of each half in case, okay, respectively. That means what the question is saying is, this is a lens, the focal length of this lens is f. Now if I cut the lens in xox, if I cut the lens in half, okay, xox and xox, then this is xox, or the focal length out here is f dash. And if I cut the lens in this half, the focal length of each of the lenses is f double dash, f double dash. Acha. In the previous slide, I have shown that the magnitude of focal length of this one would be the magnitude of focal length of this one. Okay. So first, let us deal with these two cases, f and f double dash. Okay, f double dash is nothing but cutting axis y or this axis. Okay. So between A and B, sorry, A and C, this is A, this is B, this is C. So between A and C, between A and C, between A and C, what will happen? Yeah. 1 by f for A. Okay, 1 by f is equals to mu. I'm assuming this lens is operating in A, minus 1 into 1 by r. See, I'm also assuming that both the lenses, okay, both the lenses has equal radius. Okay, so is equals to 2 by r. 1 by r plus 1 by r is equals to 2 by r. 1 by r minus of minus 1 by r is nothing but 1 by plus r, or 1 by f is equals to mu minus 1 into 2 by r. 2 by r. Achha. For C, 1 by f double dash. 1 by f double dash is nothing but mu minus 1 into, what is the radius of this surface? The radius of this surface is nothing but r, or 1 by r. What is the radius of this surface? The radius of this surface is nothing but, this surface is nothing but infinity, minus 1 by infinity. Okay, or 1 by f double dash is equals to mu minus 1 into 1 by r, or 1 by r. See, if we multiply this equation by 2, I'll get this equation, no? Okay, so can I say 1 by f double dash into 2 is equals to 1 by f? So from A and C, I can say 1 by f double dash into 2 is equals to 1 by f. Okay, or f is equals to f double dash divided by 2. F is equals to f double dash divided by 2. Okay. So from the previous slide, we got f double dash is equals to 2f. Or this option could be correct, this option could be correct. This option is wrong, this option is wrong. Now one important theory that I said, between A and C, between A and C, there's an important, sorry, A and B, there's an important theory that you have to know. A and B, there's an important theory of, what is the important theory? See, suppose this is the lens, okay, I'm drawing this big lens, doesn't mean, see, up till now I was showing lens in this manner. Okay, now I'm showing the lenses this manner. That means the rays are coming from back and going into this and going out of the screen. Okay, so suppose this is the lens. Okay, this is nothing but the aperture diameter. Aperture diameter, or diameter of the aperture. So this lens can be represented by this in this axis. Okay, this lens is out here. Out here the lens is shown like this. Out here the lens is shown like this. Okay, and this is the center. Now if I cover some area, suppose I'm covering this area with some black paint or any other opaque material, the focal length would remain unchanged. That means if I'm covering this much area with black paint, the focal length would remain unchanged. Okay. The focal length will remain as it is. But the thing is, the intensity of the image formed out here will decrease. Okay, the intensity of the image out here will decrease. And how is it related? Intensity of image is directly proportional to the area. That means intensity of an image is directly proportional to the aperture area of the lens. Which means intensity of the image formed by a lens is the area through which the light can pass through the lens. So let's focus on A and B. Out here focus of A and focus of F dash will be same. So F is equals to F dash, option number C. But out here I want to search what is the intensity of image. What is the intensity of image out here? See, half of the lens is covered, no? So intensity of this lens will be half of this. So the image formed by this lens only would be the image formed by this lens would be half as bright formed by this lens. Okay. A plano-convex lens is made of a material of refractive index 1.6. The radius of curvature of the curved surface is 60. The focal length of the lens is. What is a plano-convex lens? Plano-convex lens means nothing but one side plane, other side this one. Okay. So mu is equals to 1.6. Radius of curvature is equals to 60. So I can simply apply the lens maker formula. 1 by f is equals to mu L by mu A. I am assuming the medium is air out here. So I am always assuming mu L by mu M is equals to mu minus 1 into 1 by R1. What is the value of R1? Infinity. Minus of minus 1 by R2 or minus 60. Why? Because the radius of 2 is in this side, or minus of minus 60. Okay, or 1 by f is equals to, what is the value of mu? 1.6 minus 1 by infinity is nothing but 0, minus of minus 1 is nothing but 60, or 1 by f is equals to 0.6 divided by 60, or f is equals to 60 divided by 0.6, or is nothing but 100, or f is equals to 600 by 6 is nothing but 100 centimeter. 100 centimeter. Focal length of a convex lens of refractive index 1.5 is 2 centimeter. The focal length is given. If the focal length when immersed in liquid of refractive index 1.2 will be. Out here the lens is given. That means R1 and R2 is given, no? For this lens, wherever this lens is immersed in water or in whichever medium, the shape of the lens will remain constant. So if this surface has R1 and this surface has radius R2, the shape of the lens will remain constant. So for medium 1 by f is equals to refractive index 1.5 by 1. Okay, by 1 is into 1 by R1. 1 by R1 minus 1 by R2. See, let's name this x. Okay, let's name this entire thing as x. Why? Because it will remain constant, no? And focal length is given by how much? 2 centimeter. So this is nothing but 2 centimeter. So 1 by 2 is equals to, what is 1.5 minus 1? 0.5 into x, or x is equals to 1. See, x is nothing but 1 by 2 into 2 by 1, or into 0.5. 1 by 2 divided by 0.5 is nothing but 1. Okay. Now the focal length of the lens when it is immersed in refractive index of 1.2. See, so I got the value of x. So my new formula, 1 by focal length in liquid is equals to, what is the refractive index of lens? 1.5. But now out here the refractive index of medium would be 1.25 minus 1, and 1 by R1 minus 1 by R2 would be x, or 1 by FL would be how much? 1.5 minus 1.25 divided by 1.5. So it is nothing but 1.5 minus 1.25 divided by 1.25 into x, or 1 by FL is equals to 1.5 minus 1.25 is nothing but 0.25 divided by 1.25 into x, or 1 by focal length of lens is equals to x by 5. X by 5. Acha. What is the value of x? The value of x from previous equation is nothing but 1, or 1 by FL, or focal length of lens in medium is equals to 1 by 5, or FL is equals to 5 centimeters. So our correct option is option number C.